Okay, welcome everyone. Can you all hear me in the back? Sound okay? All right, great. So this talk is about parallelism, and it's sort of in two parts. There's a theory part and a practice part. So the theory part is about how to think about decomposing an operation so that it can be executed in parallel, and whether or not you're going to get a speed up from that. And then the practice part is about the stream library in Java 8 and how the concepts in the first part apply to the libraries that you may already be using. So how many people here are already using Java 8? How many people here are using streams? All right, great. So you're in the right place. All right, so legal disclaimer slide. That's how you know I really work at Oracle. That's sort of my credential there. Okay, so progress in chip making. This is a relatively old graph, and you've probably all seen this before. But you know what this graph shows is how the characteristics of mainstream chips have changed over time. And we've got four quantities being graphed here. The top one, the green one, is the number of transistors on a die. And this is on the bottom scale, you have time from 1970 to 2010. And on the y-axis, we have a log scale. So you see a nice, mostly straight line, which suggests an exponential increase in the number of transistors we put on a die, which you can think of as experimental confirmation that Moore's law is still alive and well. So the other three graphs paint a somewhat less pretty story. So the purple line here shows clock speed, and for a nice period of history, you got this nice exponential increase in clock speed. So all you had to do to make your program go faster was wait a few months, buy a new computer, run it on a faster computer, and you'd get better results. And this trick worked great for years, until about 2003 when it fell apart and we all didn't know what to do. And you see a similar story plays out in the lower two graphs. The blue graph is power consumption in watts, and the violet graph is what you can think of as a measure for instruction level parallelism. It's how much work can the chip do per clock cycle. And all of these things flattened out at roughly the same time, which means that we were used to Moore's law giving us a steady diet of faster chips. Moore's law didn't get repealed, but we were no longer able to use what Moore's law was giving us to give us faster cores. The best we could get out of it was more cores, right? So the reason that we have multi-core chips today is not because anybody wants multi-core chips. It's what the chip guys can build with the physical constraints that they're under. So, in the period of time from like the early 2000s, till like maybe 5-6 years ago, there was a long period of denial that, that this was actually the physical reality. But it is the physical reality, and it's been this way for, good, at least 12 years. Now, if you look at the promise of the promises that were made around 2003 of from now on we'll be seeing exponentially increased core counts. Well, how did that play out? The red line shows us how many cores we should have by now, and it's so if we're in 2006, it's somewhere on the 7th floor. And the blue dots are actually how many cores are delivered by Intel's highest end chips, like the EX chips. And so we're seeing core counts topping out at 24, 32, something like that. And the core counts you're getting in desktop, laptop grade, server grade machines are even smaller than that. So why aren't the chip makers delivering all of these cores? It's not because they can't. It's because we can't use them, right? We as software guys, we can't take advantage of, very easily even of a 32-core machine, with a few exceptions, right? There's a few corners, of the industry like data parallel analytics or, graphics where we're really able to use, a lot of cores. But for the most part, we don't really have the techniques to use all of these cores, and that's why the chips aren't giving them to us. So if you look at concurrency sort of over history, the primary goal of using concurrency has always been performance, and in particular it's always been maximizing the use of the CPU resources we have. To a lesser extent, people have used concurrency for structuring their programs. There are some really nice methodologies for using concurrency for structuring programs, like CSP or actors, which, for better or worse, haven't really caught on in the mainstream programming world. So for the most part, we use concurrency to maximize performance, although the maximization strategy has changed over time as the hardware has changed. So, in the old days when you had single core systems, primarily we used concurrency for dealing with asynchrony, doing non-blocking I/O, pushing background tasks, to a background thread so that we don't hog the processor and freeze up the the UI. And then, in the early 2000s timeframe, where we started to have machines that had 2, 4, cores, we started to use concurrency for things like coarse-grained task-based parallelism. So you've got a server application, you decide your task boundary is a user request, and you treat that as your basic unit of work, and then you farm them out to a thread pool, so that you can run each task on a different core. And that works pretty well to improve the throughput of your program. You can push more requests, through the server, as long as processing any given task doesn't run into contention with processing other tasks. As the core counts continue to improve, that trick starts to run out of gas, and we need to look for finer grained parallelism, in our tasks. And the performance target that we're aiming at shifts from throughput to latency. Can we use more cores to get to the answer faster? And can I dynamically adjust this so that if I don't have a lot of cores, fine, I'll use what I've got. If I've got a lot more cores, can I divide the problem up smaller so that I can get to the answer faster, right? So it's always been about performance, but the measure of performance that we've chosen over time has changed. As the as the hardware changes, that moves us from that sort of moves the sort of things that we can do with hardware parallelism, and the languages and the platforms catch up, right? So in the Java 1 days, Java had threads and locks and condition queues baked in from the beginning. But that was, the goal of having that was largely about being able to write thread-safe data structures. As multi-core chips became popular, we added in Java 5 the Java util concurrent library, where we added tools that made sense for that kind of computing model, thread pools and semaphores and blocking queues and concurrent collections, et cetera. And as core counts started to increase, we started to add tools, for supporting parallelism. So in 7, we added the fork join library, and in 8, we added the parallel streams that works on top of the fork join library. Okay, so just a quick note on terminology. The terms concurrency and parallelism, they don't have really good standard meanings. Some people mistakenly just use them interchangeably. Historically, if you look at the literature, from like 30 years ago, the usage was that concurrency was a property of a program structure, whether the program is structured as the interaction between cooperating activities, whereas parallelism was a property of its execution. Are there really two things happening at once, or is it only the illusion of two things happening at once? So in the old model, you can think of concurrency as being the potential for parallelism. If you have no concurrency, you'll definitely get no parallelism. If you have concurrency, maybe you'll get some parallelism if your hardware and your operating system and this library supports it. This was a useful distinction 30 years ago when there was like almost no true parallelism. It's less of a useful distinction today, so I sort of want to offer a newer definition that's gaining currency in the way this is taught, which is to say that concurrency is about correctly and efficiently controlling access to shared resources. All the things that we do with locks. We use locks to make data structures safe for concurrent access. So the basic tools that we use for concurrency, locks, semaphores, STM, things like that. Whereas parallelism is about using more resources to get the answer faster. So if you have a large data set, you partition it, you search the partitions individually, that's parallelism. Now, why does this definition make more sense than the definition that we used 30 years ago? Well, I think the reason is, when you define it this way, concurrency is still hard, but parallelism is easy, right? Writing correct concurrent code is hard. Looking at your code and making sure you have no data races, that's really hard, right? That's still something for experts. Even if you have the secret wizard spell book, it's still hard, right? We would much rather not have to use almost anything in this book, right? We would much rather be able to write code that is just so obviously correct we don't have to think about it. And parallelism is a lot closer to that because the primary trick that we use in parallelism is partitioning, right? I've got a stack of papers to grade. I'm going to grade these. You grade those. In the end, we take your pile, we put it on the top of my pile, and we're done. And there's no chance that you're going to accidentally scribble on one of the papers that I'm grading. It just doesn't happen, right? It's really easy, and we do this in the real world all the time. So parallelism, builds on techniques that are just inherently easier to reason about, inherently safer, and therefore we can use them with confidence. It's worth remembering that parallelism is strictly an optimization. It's just about getting the answer faster. And if those additional resources aren't available, fine, we'll do it sequentially, nothing lost. Now, the flip side of this is if it's only an optimization, it's only worthwhile if it actually gets us to the answer faster. And this is kind of where the difficulty comes from, because just because we may burn more cycles and generate more heat doesn't mean the computation speeds up. It might even slow down. Right, so some computations don't parallelize well. Some parallelize even, you lose by parallelizing. So, there's a cycle of, look at the problem, try to find inherent parallelism, try to implement something that extracts that parallelism, and then measure to see if you got any benefit. And the way we measure is we use a factor called speed up, which is basically the ratio of I ran it on one core, it took this long, I ran it on 4 cores, it took that long, I divide one by the other, and I get a speed up. Right? So that's a fairly simple thing to measure. Another aspect is, that is kind of obvious if you think about it, is a parallel computation will always do more work than the best sequential alternative, because a sequential execution is a parallel execution, just only, using one core, right? So the parallel computation inherently has overhead. It inherently is doing more stuff. In addition to solving the problem, which it still has to do, it also has to partition the problem and hand out the tasks to various actors and then combine the results and things like that. And that's all over and above solving the problem. So you can think of the parallel version as always starting out behind, and you're hoping to make it up in volume, right? You're hoping to get enough of a benefit from, I've got, 8 cores chewing on the same problem. I'm hoping to pick up enough benefit to make up for the fact that I had a more complicated process of partitioning and doling out tasks and waiting for tasks and merging tasks and all of that. So in order to win, we need a bunch of things. We need a problem that has latent parallelism in the first place. Some problems just don't parallelize, and at this point you're done, right? You need a good implementation that actually extracts the parallelism. You need efficient runtime support for parallelism. That's our job. And most importantly, you need enough data, right? If I want to sort 10 numbers, there is no parallel algorithm that's going to beat, a simple bubble sort. Right? Because the overhead of partitioning my data set and sorting the subpieces and merging them is going to overwhelm the amount of work to solve a small problem sequentially. So you always need enough data to make up for the overhead of just even forking off that first partition. So let's talk about exploitable parallelism. And the key takeaway here is not all problems parallelize equally, even those that kind of look like they have the same structure. And so I have 2 functions here. They both are defined recursively. So the first one, I have some function f, I don't know what it is, but I'm going to define g in terms of f, and I'm going to say, well, g of 0 is f of 0, and then g of n is, well, take g of n minus 1 and then apply f to that. Right, so I'm going to iteratively apply a function, to itself. And they have this other function, which the definition, if you step back into the hallway, would almost look the same, right? It's structurally very similar. H of 0 is just f of 0, and h of n is, well, take h of n minus 1 and add f of n to that. And what I'm trying to illustrate here, and some of you probably already see it, is that even though the definitions look the same, they're completely different in terms of how they can be parallelized. So let's take the first one, all right? So basically, parallelizing this is a total lost cause, because this is a fundamentally iterative problem. And if I rewrite it as something iterative, I'm basically saying that g of n is f of f of f of f of f of n times applied to 0. And I can't compute f of 0 until I've already computed f of 0, you know, unless I know something really special about f, which we're assuming I don't, right? So this is a fundamentally sequential problem. Another way to think about it is I have a data flow dependency, right? If you look at the data flow graph for this problem, g of 0 depends on f of 0, g of 1 depends on g of 0, and so there's no parallelism that can be exploited in this problem. So, you know, game over. Now, if we look at the other function, h, even though it has a similar structure, it's actually much easier to parallelize. And if you look at the data flow you know, dependency here, what you see is, well, h of 3 depends on f of 3 and h of 2, which in turn depends on h of 1 and f of 2. I can compute f of 0, f of 1, f of 2, f of 3, f of 4 in parallel, and then I can just combine them. Right? Now, just, you know, so this is a problem that has some exploitable parallelism. I can do a bunch of work in parallel, and then I have to do some combining work, which may or may not parallelize perfectly. So it turns out this is, you know, easy because I can rewrite it in terms of just compute these things and add them up, and, you know, compute them independently. This kind of problem is sometimes referred to as embarrassingly parallel. Now, that said, you know, I can still implement this. If I take a naive implementation that just kind of looks exactly like the problem statement, I'm going to have introduced a data flow dependency, you know, into it just as an artifact of my implementation. But I can implement it so that the data flow dependency looks like this, which parallelizes a lot more nicely. Okay, so I need to have exploitable parallelism. And I need to actually exploit that parallelism. I need to have an implementation that actually takes advantage of the parallelism, and that doesn't always come for free. So, you know, the little summary here is, you know, some problems parallelize better than others. Some problems that parallelize well can still admit naive implementations that don't exploit the parallelism. So you need to have exploitable parallelism, but that's not enough. You also have to structure your computation to exploit it. And a lot of the techniques, you know, that we generally gravitate towards when we're writing sequential programs become bottlenecks when we try to go parallel. So we have to unlearn some of our bad habits. Okay, so let's take another problem that's embarrassing parallel. I want to add up the numbers from 1 to n. Okay, so first thing we should be asking ourselves is, what kind of data flow graph do we expect that we should be able to get here? So if I write it like this, can you all read the code in the back? I'm not sure what I would do about it if you said no, but I guess it's nice to ask. So if I structure it like this, where first I say sum equals 0, and then I iterate through the array and say sum equals sum plus I, this is a sequential implementation, right? This is an implementation that doesn't really exploit the parallelism that's inherent in the problem. And I end up with a data flow graph that looks like this. I end up first computing, for the first element, and then I add that to 0, and then I compute the second element, and I add that, and I still end up with a sequential implementation. But I can do better. Okay, so you have to ask yourself, what kind of data flow graph do you want? Well, we want a data flow graph that looks more like this. Do as much computation at the leaves as we can, where I can do x1 and x2 in parallel, x3 and x4 in parallel, and then add their sums in parallel, et cetera, and the only operation that ends up being sequential is that last addition at the top, right? That's the kind of the best we can do. So how are we going to get there, right? Well, let's try a few things. So if we look at our sequential, our sequential implementation, the thing that jumps out at us is this accumulator pattern, where the first thing you say is set the accumulator to 0, and then you loop over things and you mutate the accumulator. And that should be like kind of a big flashing red light that you've got an implementation that's fundamentally sequential, and you need to unlearn this pattern because it's an impediment. Okay, so, all right. How would we solve this another way? Well, we could use a thread pool or some kind of concurrent mechanism. What would that code look like? Well, here's a broken way to do it. Imagine you had in your language a mechanism that says do two things at once. So we're going to call it the concurrent primitive, and it has two blocks in it, and it's going to just do them simultaneously. All right. Doesn't really matter how it's implemented. It's just a way of structuring the problem. So let's say we say concurrently, I'm going to loop through the first half of the array and increment my accumulator, and at the same time I'm going to loop through the second half of the array, and I'm going to use that to increment the accumulator. So does anybody see what's wrong with this? Yeah, so we got data races all over the place. Every time we access some, whether we're reading it or writing it, we have a data race. Well, that's not good, right? Parallelism is supposed to be easy, right? This is why concurrency is hard and parallelism is easy. So we're going to get the wrong answer. We clearly don't like that. So let's fix this, right? So if if you're writing concurrent code, you want to coordinate access to mutable states. So let's try fixing that with the obvious thing. Maybe you've got some locking primitive or some atomic primitive. So you wrap the thing that accesses the sum in an atomic block, right? And we're done, right? What do you think of this example? Yeah, this sucks. The performance is going to be worse than the sequential one, because in addition to doing all the work, you're doing a whole pile of locking, and every one of those lock attempts will be contended. This will be like 100 times slower than the sequential one, and no matter how many cores I throw at it, it's just going to get slower and slower. All right? So that's not good either, right? So, well, we had some exploitable parallelism, but we haven't exploited it correctly yet. So let's keep going. Now, we know, of course, that the root of all evil in concurrency is mutable shared state. So there's three ways to safely handle state. One is don't share it. One is don't mutate it. And the third choice, which should be your distant third choice, is use locks or some other coordination mechanism to coordinate access to it. So let's try to improve our implementation by using the don't share. Well, that one turns out to be really easy. So here's a first cut at a parallel solution. Instead of having a sum variable that's outside the concurrent block, I have two sum variables, a left sum and a right sum, and I make sure that the first arm of my concurrent block only touches left sum, and the second arm only touches right sum. Well, now I don't have data races, right? Because only one thread at a time, or only one task at a time, is accessing each of these variables. So this, this isn't necessarily how you would want to write it, but it kind of gives us a little, it guides us in a direction for, this is the direction we want to go in for getting there. So basically this illustrates the classic pattern of parallel decomposition, which is you decompose the problem into subproblems, you solve the subproblems independently, and they shouldn't need to share any state. And then whatever results each one has come up with, you combine it, which is what that last line does. Take the left sum, add it to the right sum, and that's the answer to the problem. So that's, this is how basically all parallel algorithms work. So, okay, so how is this going to perform? Well, if I have enough data, it's going to perform just fine with one core. It's going to perform pretty well on two cores. And above two cores, I'm not going to see any speed up because I've only cut the problem in half. So I'm only keeping two cores busy. So obviously, I need a little bit more help in my partitioning approach, but the structure of it looks good, and I don't have any shared access to mutable states, so we're making progress. So the generalized form for pretty much any parallel algorithm is a divide and conquer approach. So the idea is you recursively decompose the problem into smaller and smaller and smaller subproblems until the subproblems are so small that it makes more sense to solve the subproblem sequentially. So, for a given problem, you say, is the problem already small? If it's small, just solve it. If I'm sorting things, if I have fewer than 50 elements, I'm just going to, sort them sequentially. Otherwise, I say, divide the problem in half, and then recursively call myself to solve the left subproblem and the right subproblem, which might recursively get decomposed more and more and more. And then when the two of them finish, I do whatever I have to do to combine the results, and I'm good, right? And so this addresses the issue in the previous example where you were only dividing the problem into two, so the best you could get was a 2x speedup. Theoretically, each core could be kept perfectly busy with some chunk of the original input, and you should be able to get good parallelism here. Does it make sense to everybody? Okay, good. So The nice thing about recursive decomposition, as long as you understand recursion, is it's really simple, right? And a lot of our data structures are already defined by recursion. If you've got a binary tree, everything about binary trees are already defined by recursion. So it makes a lot of sense to have the structure of your computation and the structure of the thing that you're operating on be the same. We have no shared mutable state, we're just partitioning. You add up those numbers, I'll add up these numbers. That's really easy. And the other thing is, that's less obvious is we start forking off work as early as we can, right? Because whenever we start a parallel problem, we're only on one core. Nothing ever starts out in parallel. And there's always a certain amount of time lag to when I say, here, you do this part of the problem, between the time I try to hand it off and the time the other worker takes the handoff, right? So you don't want to do like a lot of partitioning work up front and then hand out the pieces. You want to start dividing so that the first worker divides it in two and hands something to a second worker, and now both workers can be dividing things into fourths, and then four guys can be dividing things into eighths, et cetera. And you start getting, you start all the workers actually doing something as early as possible. This is what keeps you from being on the wrong side of Amdahl's law. If you have a big sequential step to partition the problem, if you have 64 cores, every cycle you spend setting the problem up is 63 cycles you're not using computing, right? So the other cool thing about recursive decomposition is it's dynamic. There's nothing in the code that says decompose it 5 times and then stop. It's keep decomposing until the problem is small enough. And we can incorporate into our, should I go sequential or should I decompose some more, in addition to saying, I don't want to do that if the problem's too small, I can also at runtime look at how many cores do I have? What load have I already put on my parallel task runtime? If all the cores are busy and they all have a long queue of tasks to chew on, I shouldn't decompose anymore. I should just start computing, right? And so you can dynamically decompose based on what resources you have, but the code that you wrote is completely portable across core counts. It could work on 1 core, 2 cores, 1,000 cores, 1,000,000 cores, doesn't matter. So that's pretty nice. Okay, so to apply this to a simple example, let's say we've got an array of numbers and we want to sum them up, and obviously I wouldn't use parallelism for 8 numbers, but the slide would have to be really big in order to show this at life size. So the first thing I'm going to do is I'm going to divide it into half. I don't actually copy the data. I'm just passing the indices, right? So I have a big shared array somewhere, and I say, okay, your items number 1 through 4, your items 5 through 8, go, right? And they are recursively going to do the same thing and divide up, their chunk into smaller chunks and pass them on to other tasks. And then we actually do the work, right? And the reason I've written the work this way is hopefully you're thinking back to when you were in elementary school math and you're thinking, that kind of looks like associativity, right? The key to being able to parallelize something is associativity. Anybody remember what associativity is? It means grouping doesn't matter, right? Now, when you were in 5th grade math and they were teaching you this and you're thinking, when am I ever going to need to know this? That day's here. It's been a long time, but we got there, right? So because addition is associative, it means I don't have to add them all up in order. I can have this guy adding 5 and 6 together and this guy adding 7 and 8 together and combine those without having to start from 1 plus 2 plus 3 plus 4 plus 5, et cetera. So each worker adds up, the numbers they've got. And then we propagate this, we replace them with the sums, and we start to propagate those sums upwards, and this is all happening in parallel. And the only really sequential step is this last one, where you're adding up the last 2 numbers. Okay, so that's recursive decomposition. Almost every parallel problem looks like that. They're just not all as well behaved as addition. Okay, so how can we look at a parallel problem and have some intuition about whether we're going to get a speed up from parallelism or not, right? Because if we're not going to get a speed up, we shouldn't do it, right? It's purely an optimization. So you can think of, there's all of these different sources that kind of rob you of your potential speed up. So one of them is, how efficiently can I split the problem? If it's cheap to split the problem, then that's good because, I can be doing useful work very quickly. If it's expensive to split the source, then that's going to take time away that I could be doing actual work. Similarly, if I'm sending messages to activities that are running in different threads, there's a cost here. There's a cost to creating tasks. There's a cost to scheduling tasks. There's a cost to waiting for a task to complete. There's a cost for asking a task for its result. I can do a lot of work in the time it takes to hand something off to another task. So if I'm going to hand something off to another task, I want to make sure that the benefit that I get from us both working at the same time is going to exceed that cost. Similarly, if I divide a problem in two and I solve the subproblems, I still have to combine the results. If the problem is something as simple as adding up numbers, then the combination is really simple. Add the left result to the right result. That's really cheap. But what if my problem is constructing a hash map? Now I have two hash maps that have to be combined. I have to construct a new hash map that is the fusion of those two other maps. That can be a pretty expensive combination. There's also locality, which is kind of frustrating because you can't see it in your code, right? You can see the cost of combining two hash maps in your code. What you don't see in your code is locality, right? If I have an array of numbers and I'm adding them up, hardware loves this, right? Because I'm accessing them sequentially. I pull the first number into cache. I've already pulled the next 15 numbers into cache. And by the time I'm on the third number, the prefetcher has kicked in. It's like started to pull the next, the next set of numbers into cache. So I'm likely to lose very little time waiting for the memory management subsystem to cough up data and a lot more time actually computing stuff. If I have bad locality, if every data item requires multiple pointer fetches, then maybe what I'm going to end up with is 16 cores all sitting around waiting for cache misses, and I'm not actually going to get a speed up from that. And you can see this if you use the streams library and you say take an array of ints and then do a reduce over it and you sum them up, and then you take an array of boxed integers and you sum them up, and you do it in parallel, what you'll see is you'll get almost perfect speed up with summing up the ints. You'll get almost no speed up with summing up the boxed integers because your 4 or 8 or 16 worker threads are spending all their time waiting for data and no time adding up numbers. So you don't get any parallelism benefit from that. So you can think of each of these things as, if none of these things go wrong, then you'll get some parallelism. Each one of these is trying to steal your parallelism. And, and they all chip away at your potential speed up. So, you need to have reasonable characteristics on all of these things, and you need to have enough data to make up for the overhead of getting the whole thing started in the first place. Okay, so how many people here have used the fork join library directly? Okay, great. So in Java 7, we added the fork join library. It's not so easy to use. It's very fast, it's very flexible, not easy to use. So you can think of it as, just as like the thread pools we added in Java 5 are a good task management mechanism for coarse-grained tasks. This is for fine-grained CPU-intensive tasks. So if you're going to be doing I/O, fork join really, probably isn't the right substrate for it. But if you're doing compute-intensive stuff, it works pretty nicely, and it scales pretty well from to the tens and hundreds of threads, and it's all optimized for divide and conquer. All the research behind it is 20, 30 years old. It's all from the Silk. It's all based on things we learned from the Silk project 20 years ago. But basically, it's all designed to minimize contention cost and not introduce a lot of overhead for task management. So basically, the two operations the fork join gives you is fork off a task and wait for a task to complete, fork and join. Right? So you can think of this as a substrate for that mythical concurrent abstraction that I had in the earlier examples, where you're saying, do these two things in parallel and wait for them both to be finished, and then I'll get the results and I'll combine them. Okay, So because fork join is powerful but hard to use, streams is layered on top of fork join, which is easy to use. So streams is about possibly parallel aggregate operations on data sets. And your data set can be anything. It could be a collection, it can be an array, it could be a generator function, it could even be an I/O backstream. And we've gone out of our way to weave in support throughout the the JDK into all the collection implementations so that any of them could be a source for a parallel computation. Now, one of the nice things about streams is it encourages you to specify your calculation declaratively. What do I want to calculate rather than how do I want to calculate it? And that's what allows the runtime to be able to do a calculation either sequentially or in parallel off of the same specification. And we build up stream pipelines from some pretty simple primitives, filtering, mapping, sorting, reducing, and there's a lot of cool implementation tricks under the hood in streams. I could do a whole talk about that. But what's really relevant here is any operation can be done in parallel. So any stream pipeline, you could say, do it in parallel. That doesn't mean you'll get a speed up when you go parallel. You might even get a slowdown, right? It's not magic parallelism dust. And this was one of the sort of pedagogical challenges that we faced when we first shipped this library is everyone wanted to put .parallel everywhere. And it didn't take too long before they concluded that Java 8 sucks. And that wasn't the conclusion that we wanted them to reach, but we kind of knew we didn't have a lot of control over that. But what we're trying to the message that we're trying to get out is, if you were in a position to be able to analyze whether parallelism will be ineffective in a given problem, we make it really easy to say, let's turn this calculation parallel. But that doesn't mean parallel is the right default. Okay, so. You've all seen streams, but here's our classic example of typical ad hoc Java code that, you don't even know what it does until you've spent 15 seconds reading it. And if you rewrite that as a stream pipeline, it's really obvious what it does, right? But the cool thing is, not only is the code on the right more readable, but it's a lot easier for the runtime to analyze it and do really cool things with it and say, oh, you've got a sorted stage in your pipeline here, but I know at this point the data's already sorted, so I'm not going to do any sorting, right? There's no way that we could take the code on the left and figure that kind of stuff out, but it's really easy to do that to the code on the right. So the code is nicer to read and nicer to write, but it's also much nicer to optimize. So everybody wins. Okay, so let's say we want to use parallel streams. How do we know whether we're going to get good performance out of it? Well, so we had a bunch of factors that steal away from parallel performance, in an earlier slide. Let's apply them all to streams. Splitting and decomposition costs. How well does your source split? Well, your source could be a collection. It could be an array. It could be a generator function. It could be anything. And the way a source is defined is you can ask it to split itself. And sometimes it'll say, no, I can't split any further. And sometimes it'll say, okay, yeah, fine, here's my first half or whatever. So some sources split better than others, right? So you have to look at where your data is, where it's coming from, and whether it's going to split well. Dispatch and task management costs, that's pretty much handled by fork joins, so you don't have to worry about that too much. Combination costs, you should be able to look at your code and say, is my combination step cheap or expensive? Am I adding up numbers? Am I taking the max of two numbers? Or am I merging two hash sets? And similarly, we have to reason about locality. Array-based sources parallelize better than anything else. Big surprise, because arrays, get great locality. So let's kind of let's build a little bit of a model for thinking about parallel performance, and then we'll drill into each one of these. So you can make arbitrarily complicated models for parallel performance, but I think the simplest one, which helps you eliminate a lot of the non-candidates very quickly, is what I call the NQ model. It has two parameters. N is how many data items do I have? Q is how much work am I doing on each data item, right? So if I multiply these together, I should get the total amount of work that I'm going to do. Right? I'm going to do, Q amount of work on N things, so N times Q is how much work am I doing in total. And the rule of thumb is is this more than 10,000? And what you're all thinking is, well, I know what n is denominated in. What's q denominated in, right? You know, electron volts, byte codes, machine instructions, lines of code. What I'm going to say is, it doesn't matter. Just pick something, right? You know, adding up two numbers, addition, call that 1, right? Sorting a list, that's a lot more than 1, right? You know, you should be able to look at your pipeline and say, at each stage, I'm really not doing anything. I'm shuffling some data around, I'm adding things up. That's a low Q problem. Or at each stage, I'm like factoring large numbers. That's a high Q problem, right? And so, you know, this is not meant to be so much as a numeric model, although, I mean, you can make it into a quantitative model, but it's really more a way of eyeballing the problem and saying, do I have enough data that, you know, this is going to work? So if I'm, you know, just like picking out the maximum element out of, you know, an array of integers, if I have, you know, fewer than 10,000 elements in my array, I'm probably not going to get a speed up. So, you know, good rule of thumb. Okay, so let's look at each of those sources of inefficiency and see how they apply to streams. Since they're finished over there, I have to talk faster, even though we still have 20 minutes left. But I'll talk faster anyway. Some sources split better than others. So, you know, and you know, when I say better, it might be cheaper to do the split. Splitting an array is really easy. Find the midpoint, compute that index. Low plus high over 2, easy. A better split is one that's more even. A better split is one that's more predictable. So if I have an array, this splits cheaply, it splits evenly, and I know perfectly what the sizes of my chunks are. A linked list is the worst thing, right? How do I split a linked list? First, rest. Okay, now I'm going to split the rest. What do I do? First of the rest of the rest. Right? I can do this, and if my Q is high enough, I can get parallelism out of this, but it's a lousy split, right? And if I have an iterative generator like the G in my first example, that behaves like a linked list, because you can't get to the second one till you've done the first one, okay? Whereas a stateless generator behaves more like an array. So, you know, this one showed up as a performance puzzler in the very early days of streams. Someone wrote the first, the first one as an expression of add up the numbers from 1 to n, and they said, why am I getting terrible parallel performance? And I said, look at your source. You can't split that. All you can do is first rest, and then, you know, do that iteratively. Whereas if I express it as a range, which is like a stateless generator, that splits perfectly, and that parallelizes perfectly, right? So look at your source and ask yourself, how does it split? Arrays split great. Array lists split great. Linked lists split terribly. Binary trees split okay. They're not as good as arrays because I don't necessarily know exactly how big the left half is versus the right half, and if my tree isn't balanced, maybe one half will be bigger than the other, but they split okay. Okay, similarly, let's look at locality. And like I keep saying, this is the elephant in the room. Parallelism wins when we can keep the CPUs busy. Waiting for a cache miss is not keeping the CPU busy. That's keeping the CPU stalled, okay? On a lot of systems, most systems that cost less than $20,000 to $30,000, your limiting factor is always going to be memory bandwidth, right? You may have a lot of CPU power, but the rate at which the memory subsystem can keep all those cores fed with data is going to be your bottleneck. So if you have your data in arrays, these parallelize really nicely. And here's the example I told you earlier, stream of interarray.sum versus stream of integer.sum. And I'm only looking at speed up, you know, so if I have 1,000 elements, well, I don't get any speed up, but I don't really lose anything either. If I have 10,000 elements, I got like a 6x speed up. This is on an 8-core machine. With 1,000,000 elements, I got almost an 8x speed up, right? Pretty good. What did I get from my 1,000 elements with the, the boxed integer? I got a 5x slowdown, right? And even with 10,000 elements, I barely got a speed up, right? I'm spending just way too much time waiting for data. Okay, so when I talk about locality, this is what I mean. If I have an array of integers, in order to get to each integer, I have to traverse a pointer, potentially taking a cache miss. If I have an array of ints, They're all right there. If I've pulled in 3, then 9 is right at hand. Okay, and so this is something that's in your, you can sort of see this in your code if you look carefully, right? How many dots are there, right? It's kind of implicit, but at least it's there. Okay, here's another factor that affects parallel performance: encounter order. What do you do in your stream pipeline? What operations are you performing? Are you doing simple things like mapping and filtering, or are you doing things that are tied to encounter order? Now, what encounter order is this is the order that's implied by the source. Some sources have a natural encounter order, an array or a list. They have a first element and a second element and a third element. A hash set does not have an encounter order. You can iterate it and you'll get elements in some order, but the order isn't meaningful. And there are some operations like limit and skip and find first whose semantics are tied to encounter order, and what that means is that gets in the way of parallelizing, because if I'm saying I've got this big stream and I want to find the first element that has some property, well, I can decompose my source and apply that property in parallel, and let's say I discover that the 12,000th element has that property. I can't say I'm done until I've evaluated it for all the elements first, because I want the first one that has that property. So things like find first are inherently parallelism hostile. Now, it may be that your source has an order, like it's an array, but the order isn't important to you. Maybe you just want to find an element with that property. So what you can do is you can do one of two things. You could use find any instead of find first, or there's this stream operation called unordered, which means take the stream and turn it into an unordered stream, which means just ignore the fact that the order has any effect. And then the stream library will optimize based on, well, if order doesn't matter, I'm not going to tie the implementation to the assumption that I have to really give you the first one, because first doesn't mean anything here. So if you have operations like limit, skip, find first, which are inherently tied to encounter order, you know, watch out, this is a source that steals away your parallelism, and if that's not what you, if the problem you're trying to solve is independent of encounter order, just make the stream unordered. You'll get better performance. Okay. Last one on our list was merging, right? So some operations, some really cheap to merge, others like grouping by to a hash map, really expensive to merge. They involve a lot of data copying, you know, and like if I do a parallel decomposition and I end up with a hash map at each leaf, then I have to like combine them into a bigger hash map and then combine those into a bigger hash map, and there's a lot of data copying going on, and this often overwhelms the parallelism advantage we get. So, you know, like if I try to parallelize collecting to a set, you know, I saw a pretty significant slowdown because I was losing all of my performance to, you know, to merging maps. And, you know, you can sort of see what that looks like, right? If I have, if I want to create a set from the first, you know, n elements, so I create a set at each leaf, and then I have to merge those two sets into a bigger set, and I do the same thing over here, and then I have to merge those sets again. It probably would have been easier to just make one set at the top in the first place. So any of these factors can conspire to undermine your speed up. Do I not have enough data? Is my NQ not high enough? Do I have too many indirections? Am I spending too much time cache missing? Does my source just split badly or not at all? Some sources don't split at all. Does it cost too much to combine the results? Or does my pipeline use operations that are sensitive to encounter order? With sort of this checklist, you should be able to like look at a parallel stream pipeline and say, I have a pretty good idea whether this is going to parallelize well or not, right? It's not black magic, right? It's you go through the checklist and you should be able to, I mean, you may not be able to like exactly predict the speed up, but you can look at it and say, this is going to be pretty good, or this one's going to suck. And the ones, you know, the ones that are going to suck, you don't even bother measuring them, right? Don't try to make them parallel. You know, but the ones that sort of pass all of these filters, those are candidates for parallelization. Okay, so let me just sum up here, and then I'll have time for some questions. Streams are cool, yay. Parallelism is cool, yay. But parallelism isn't magic. Parallelism is an optimization, and parallel streams are not magic performance tests. So, like always, before optimizing, if you remember nothing else from this talk, remember this last bullet point. Before optimizing, have performance requirements. If you don't have performance requirements, your code is by definition fast enough, and optimization is by definition burning your employer's money. If you haven't invested in having performance requirements, then you shouldn't invest in performance tuning. Okay, let's say you have performance requirements. Have good performance measurements. If you don't have good performance measurements, then optimization is mostly an exercise in self-entertainment, right? Which is fine, but don't do it on your employer's time. And make sure that your measured performance falls short of the requirements before you start optimizing, right? If it's fast enough, it's fast enough. If you have good requirements and you have good measurements and you're not fast enough, then by all means, apply this stuff and see if that might get you out of your performance problem. And with that, I'm happy to take questions. All right, we'll start over here. Just shout your question out and I'll repeat it. We won't wait for the mic.
So fork join has a way of specifying the number of CPUs you want to divide it up to.
Right.
Is there a way of doing that with a parallel? Say parallel for 2 cores or something?
Yeah, so the question is, can I have control over the parallelism I'm asking for with streams? And the short answer is no, and I'll explain why the answer is no. The one thing you do have control over is all parallel stream operations are done in a common fork join pool. So it creates a VM-wide fork join pool. The number of threads by default is based on the number of cores you have, and then there are some system properties that you can use to sort of tune those up or down. And a lot of people, when they first look at this, they say, can I specify my own fork join pool? And we say no, and they say, why not? And we say, because we know what's going to happen if you do that. And here's what's going to happen if you do that. You're going to make a fork join pool, and he's going to make a fork join pool, and she's going to make a fork join pool. And in the aggregate, you'll have 8 cores, you'll have 2,000 threads competing for those cores. And you'll get lousy performance, and you'll say Java sucks. So the flexibility of doing that becomes a kind of tragedy of the commons. And having a single pool where all of this stuff is going on allows us to keep the cores busy without a lot of scheduling overhead. Most of the time, the properties we use to tune the size, most of the time people use to make the pool smaller, because you're saying, I got 16 cores, but I'm running 4 JVMs on this machine, so I don't want them each spinning up 16 threads. Let's have them each spin up 4 threads. But it's a system-wide property. Question over here.
Is there a way or any plans to have a core affinity?
So the question is, what are we doing about core affinity? Not a lot right now, is the honest answer. Most of that is most of the work going on with core affinity is at the operating system level. Because Java is portable across so many different operating systems, it feels like a game of whack-a-mole to try to expose that up at the Java level. But ask me again in a few years, I might have a different answer.
I will.
Okay. Got a question over there in the black shirt.
Do you think it would be possible for the language to determine when to parallelize rather than language?
So the question is it possible for the language to determine when to parallelize? So a couple of things have to happen. First of all, the language has to be able to determine that it is safe to parallelize. And that's a really hard problem in a language where mutability is the default. And where you have virtual method calls where you don't even know what data is going to be touched by whatever implementation at runtime of that method is going to be executed. So even determining whether parallelism is safe is pretty hard to do. And then further determining that it would be effective is even harder, right? So there was a lot of research in the 80s and 90s about auto-parallelizing Fortran compilers, which was comparatively a much simpler system. And well, a lot of people got PhDs. But the end result, for the computing industry was not that positive. So it seems like getting some hints from the programmer of I'm going to start doing a really data parallel thing doesn't seem like a lot to ask. So that's the direction that we've taken. All right, question in the back there.
If you have work that is not like what you've described, that is, I/O work, databases, or recommend still red pools then?
Yeah, so the question is, what if I'm not doing data parallel stuff? What if I'm doing, like I'm making requests to a whole bunch of, different servers, and I'm going to then, make a composite web page based on images that came from 100 places or something like that, right? So that is sort of a good use case for the sort of Java 5 era thread pools, work queues, semaphores, kind of concurrency tools. Because you're spending most of your time waiting, and when you provision thread pools like in a web server, you typically have 100x as many threads as you have cores, because most of the tasks are going to be spending most of their time waiting for I/O, either from the requester, sending data back to the requester, to a web service, to a database, et cetera. And so the assumption is you're not very CPU intensive, so we're going to provision a lot of threads. That works pretty well. Now, a bunch of people have complained, quite rightly, that, gee, I'd like to be able to use something like parallel streams, but I'd like to give a hint that says, the tasks I'm going to do in this parallel stream are not compute intensive. So use different heuristics about how fine to slice the tasks and how much to split. And that's a totally reasonable thing to want to do, and it's something we would like to address, to be able to pass like a parallelism policy that talks about how aggressive to be about splitting and things like that, which would go a long way to helping I/O intensive parallel operations. We just haven't gotten to that yet, but there's no reason why we couldn't. One more question here?
Talk about potential for affinity and ergonomics. Is there anything else really interesting in the future streams that we should start learning about?
So the question is, what else is coming down the road with streams? And for the most part, we think streams is in decent shape. Over time we'll add some optimizations, we'll add some more operations, but at this point, streams is almost like a library that any of you could write. It's not magic, it's just a library. So our goal for streams, in some sense, it was a validation for the language things that we were doing, that it was practical to write libraries like this. We using the Java 8 language tools. But once we kind of demonstrated that, we don't actually need to be in that loop, right? There's lots of other libraries out there, and if you look at also to speak to this gentleman's question, if you're doing like reactive stuff where what your computation is based on is not, I've got a bunch of data in a data structure, which is kind of the focus for streams, but I've got a stream of events coming in from somewhere, and I want to filter them and group them and all of that. There's libraries like RxJava, which they look a little bit like streams, but they're designed around the assumption of my data source is infinite and asynchronous, as opposed to my data source is sort of like a cache miss away. So I think the action is mostly going to be in people building new libraries for things that streams isn't perfect for, and I think that's great. So, I'd like to get out of this business because I think we've kind of succeeded here and focus on enabling things in the language in the VM that are that next round of pain points for people writing cool libraries like this. So, do we have time for one more question? Yeah, I think we do. Okay, we had a question in the back there. Can you stand up so we can hear you?
With lambdas, are they run concurrently? And if so, is anything done with data races?
So, all right, so the question is, I'm passing a bunch of lambdas to my stream operations. What's the concurrency story here? And the concurrency story is straightforward. When I'm doing filtering, mapping, what have you, whatever thread is doing the filtering or mapping just turns around and calls the lambda, right? So if your lambdas have data races, your stream pipeline will have data races. Now, if you read the specification for the streams library, how many people here read the specification of libraries before they use them? Whoever's raising your hand is lying. So if you were to read the specification, which actually does exist, it will say things like the parameter that you pass to filter should be a stateless lambda. Okay, what does stateless mean? Stateless, it means it should not access any state that's going to change during the course of the stream pipeline. If it does, and you run this in parallel, you may get the wrong answer, right? So, we can't control what state you're going to access. All we can say is, you pass some behavior to this method, and it's going to invoke that behavior. If you're accessing data, then you're on the hook to either make sure that you have exclusive access to it or that you're coordinating properly. Ideally, you'd like to be, not accessing any shared mutable data, because then you have to coordinate and you lose all your parallel benefit. So, it's a little bit tricky grafting a sort of functional style operation onto a mutation-happy language like Java, right? And when we wrote the specification, we went around and around trying to figure out what the right terms to put in the spec were. Was it side effect free? No, actually side effect free wasn't the right term. Was it pure function? No, pure function wasn't the right term either. Those were the obvious choices. They turned out to be wrong. We had to invent a ridiculous new name to actually describe what we meant. Because you have no idea what's going to touch what data, right? And so we tried to pick something that allowed harmless side effects like logging, but excluded doing things like stateful accumulation. And that's what we ended up with. And it's the same thing with the data source, right? If you have one of these lambdas that goes and mutates the data source, that's the source of your stream, well, things are going to blow up, right? Unless your source is already a concurrent source. So we tried to spell that out as much as we could in the spec. So, all right, I think that's all the time we have. Thank you very much, everyone.